We're going to talk about log properties. Log properties are things that are always true about logs that we can use to help us to solve problems. So we'll look at our first property, and this is known as the product property right here. The product property says that the log base b of the product of two numbers is the same as the log base b of each of those numbers added together separately. So log base b of x plus log base b of y is log base b of x times y. Let's look at an example of this. Log base 2 of 4 is equal to 2 because 2 squared is 4. So we're saying what exponent do I put on 2 to get 4? Log base 2 of 8 is 3. 2 plus 3 is equal to 5. And log base 2 of 32 is 5. Also notice that 4 times 8 equals 32. So the number inside is the product of these two arguments, 4 and 8, and you add together their logs. This is a direct result of the log prop or the exponent rule that says 2 squared times 2 to the third equals 2 to the fifth. Notice what we're doing with their exponents is we're adding the exponents. 2 squared times 2 to the third equals 2 to the fifth. 2 plus 3 is 5. Logarithms are exponents, so what we're doing here is just adding exponents. So that's where this rule comes from. If we look to the next one below, this is called the quotient product. Basically, same type of idea, only instead of multiplying and adding, we're dividing and subtracting. So for example, we could say log of 27 over 3, log base 3 of 27 over 3 is log base 3 of 27 minus log base 3 of 3. Well, let's just think about this is the same as log base 3 of 9. So this is 2. So I'm just going to write on here, this is log base 3 of 9. So this whole thing equals 2. Log base 3 of 27 is 3, and log base 3 of 3 is 1. So basically, when we say 27 over 3, this is the same thing as saying 3 cubed divided by 3 is 3 to the 3 minus 1, which is 3 squared. So we're subtracting the 3 minus 1 to get 2. We're subtracting the exponents because all of these are the same base logs. And notice they do have to all have the same base for this to work. So where does this come in handy? Why do we even want to know these little rules? It's because when we solve problems involving logs, so the purpose is to solve equations here. So if we want to solve this equation, we have log base 3 of x plus log base 3 of x minus 2. I can rewrite a log problem into exponential form, but only if there's a single log. So this allows me to combine two log expressions together into a single log. What I did was I recognized this product property that a log base 3 of x plus log base 3 of x minus 2 is the same as log base 3 of x times x minus 2, which gives me the x squared minus 2x in the argument here. This is one where we're subtracting the logs. This is log base 10. Log of x plus 5 minus log of x is log of x minus x plus 5 over x. So we just divide their quotients. And this, once again, allows us to write two log expressions down into one. And this extends to multiple ones. So if we have 3 or 4 added together, or 2 added and 1 subtracted, we can combine them together in multiplying and dividing multiple logs. So for example, if I had log of variable, I'm going to name a few variables here, log of c plus log of a plus log of b plus log of I plus log of n, I can say these are all added together, so that's the log of c times a times b times I times n. And I have log cabin. Ha! One of my favorite math jokes. Don't tell the next class because I want it to be a surprise. Okay, let's go down to the next one down here. This is known as the product property, but I like to call it, just kind of casually, the rainbow rule. And the reason I like to call it the rainbow rule is because this exponent, if I take log base b of x to the p power, so I've got an exponent inside the log here, I can bring that exponent out and put it up in the front and multiply the whole log by that. So hence a rainbow. Okay, so let's look at an example here. Log base 2 of 4 to the third. I can rewrite that as 3 times log base 2 of 4. So this is log base 2 of 3 to the third is 64. And this is 3 times log base 2 of 4. Log base 2 of 4 is 2. And this turns out to be 6 then. 6 is 3 times 2. So log base 2 of 64 is 6. This is kind of like raising a power to a power. So that's kind of how that goes. But notice here, this is really helpful in particular when I have a problem where the variable I'm trying to solve for is the exponent of a quantity that's inside of a logarithm, because I can't solve for that unless I can get it out of the logarithm. So I can take this 2x and move it out front, and so now I have 2x times the natural log of e, and the natural log of e is just equal to 1. So it'd just be 2x. Here I have an example of this exponent can be brought out front. Notice to put it in parentheses, that's very important. X plus 1 times log of 3. Well, log of 3 is just a number. I can figure that out. I can distribute it. This just becomes linear once I do this. So this really helps a lot when solving problems. Another property that is a little less important now than it used to be with the technology we have is what's called the change of base formula. Two bases that are very common are log base 10, just log, and log base e, natural log. And I am allowed to rewrite something that is a less common log base 3 of 5, as log of 5 over log of 3, or natural log of 5 over natural log of 3. Notice that the base becomes the log in the denominator and the argument becomes the log in the numerator. And notice I can use any base with this. Sometimes it's helpful to use a clever choice of base. Log base 8 of 16 is not something that I could figure out in my head because I don't know what 8 to what power is 16. But I notice that 8 and 16 are both powers of 2. So I'm going to say log base 2 of 16 in the numerator and log base 2 of 8. So I picked a different log that's just a nice handy log in this situation. I know that log base 2 of 16 is 4, and I know that log base 2 of 8 is 3. So the answer is that 8 to the 4/3 power is equal to 16. A few other log properties that are just helpful for rewriting things. Just to remember that these are actually just some characteristics of logs. Log base b of b is always 1, and log base b of 1 is always 0, because b to the first equals b and b to the 0 equals 1. Log base b of b to the a is equal to a because b to the a power equals b to the a. Okay. Log base, or b to the log base b of a equals a. If I rewrite this in log form, I'm saying log base b of a equals, so I'm saying this, here's my base, here's my exponent, here's my answer, equals the exponent, log base b of a. Now I want to show you just an example of this one. So I'm going to take this over here and show an example. So let's say we have 2 to the log base 2 of 8. And I want to know what that equals. So we'll just call that x. Well, let's think about what log base 2 of 8 is. Log base 2 of 8 is 3 because 2 to the third is 8. So this becomes 2 to the third, which is just 8. So if these two bases are the same, then these two equal each other. So that's what we're seeing here. B to the log base b of a equals a. couple other things to remember is that you can't take the log of 0. You can't take the log of a negative number. There's no way to raise a base to any power and get 0, a positive base, or get a negative number. A log base must be positive and must not equal to 1. If you want to know why it can't equal 1, I'll tell you. If not, just shut off the video and I'll stop here. But if you're interested, listen for a couple more minutes. Nothing I'm going to test you on. So let's say we have log base 1 of x equals y. And let's make some table of values here. And we remember that log base 1 of x equals y means 1 to the y equals x. So I'm actually going to pick values for y and find x. So let's make y 2. 1 squared is still 1. Let's make y 1. 1 to the first is 1. Let's make y 0. 1 to the 0 is 1. Let's make y negative 1. Well, 1 to the negative 1 is the same as 1 over 1 to the positive 1, and it is still 1. 1 to the negative 2 is 1 over 1 squared, which is still 1. So basically, no matter what I put in for y, I get 1 for x. So if I graph this, the point 1, 2, the point 1, 1, the point 1, 0, the point 1, negative 1, and the point 1, negative 2, and I could continue on, I have a vertical line. So not only is a vertical line not a log function, it's not even a function. So that's why the base can't equal 1. Now, a negative base is problematic because if I raise a negative base to an even power, it becomes positive. If I raise a negative base to an odd power, it becomes negative. So instead of a nice smooth log graph, I have a crazy thing that jumps up and down, above and below the x-axis, and it also will not look like a log graph.